Welcome to lecture 40. In this lecture, I will be talking about the so-called Casimir effect. Recall that in lecture 39, we revisited the partition function in temporal axial gauge, and we found for the U1 partition function, z is equal to minus e to the minus 1/2 sum over the Euclidean four momenta k times the logarithm of k squared squared. The power 2 in the argument of the logarithm was coming from the fact that we had two physical polarizations of the photon that were giving rise to this partition function, which is a physical observable. The other two polarizations were canceling out. The sum in the exponent of the partition function is over all Euclidean four momenta, omega n, and spatial wave vector k. In this lecture, we will use this expression for the partition function to study the Casimir effect. What is the Casimir effect? Basically is an application of quantum field theory to a system that has non-trivial spatial boundary conditions. In particular, for the case at hand, what we are interested in is revisiting the partition function now in the case where we have two conducting plates, which in the simplest case here we assume to be infinitely large and parallel to each other. And because of these plates, the boundary conditions that we have to use will be different from the infinite volume free boundary conditions that we considered in the previous lectures. So this is essentially quantum field theory in a finite volume. The result of that calculation will be that the result of the partition function will change if we have these non-trivial boundary conditions. So we get a prediction of what the pressure between these plates should be. And as a consequence, we can make a testable prediction for this particular system, electrodynamics, in the presence of two conducting plates. Because we are now looking to study quantum field theory in a finite volume, there are a few differences with respect to the treatment we have been using so far. The case at hand, we have special boundary conditions in the spatial direction. Let's take the plate condition, which we sort of take them to be sort of separated in spatial direction z. So we put one plate, for instance, at z0, and the other plate at z is L, where L is an arbitrary parameter. And if these are conducting plates, then we want to have the parallel component of the electric field and the transverse component of the magnetic field to vanish at those two locations. The pressure and the free energy differences, the pressure and the free energy will differ in a finite volume. So far, we associated the pressure with minus the free energy. The free energy is always given as minus the logarithm of z divided by beta v. And for infinite volume, that's the same as the pressure. However, the fact that we now have a finite volume gives us a different result. Namely, it's that the pressure should be the derivative of the logarithm of z with respect to the volume. And while these two expressions sort of lead to the same thing when the volume is going to infinity, they generically will differ if the volume is finite, as is the case with the plates separated by distance L. So let us investigate this particular boundary condition of the conducting plates for now. We said that the parallel component of the electric field and the transverse component of the magnetic field have to vanish. Because of this, we find that the gauge field components at these two locations also have to vanish, and this will give conditions on our momenta. If we do a usual Fourier transformation, writing now only the direction in which we are interested in, namely only the z direction, we can write the gauge field as 1 over the length of the direction, 1 over L, times the sum of the wave vector in the z direction, e to the ikz times c times the Fourier components in this direction. For now, all the other directions remain unchanged. So we only concentrate on the one direction that we expect a difference. The gauge field is real. So that means that some of these components here must cancel out. In particular, we can write AZ as the cosine of KZZ times the real part of A minus the sine times the imaginary part of A. If we now use one of these boundary conditions, namely that the gauge field at Z0 has to vanish, we plug this in on the right-hand side, we find that the sine vanishes at Z0, the cosine at Z0 is just 1, and we find that A of 0 equal to 0 can only be accomplished if the real part of the Fourier components A tilde identically vanish. So there's one boundary condition. And the other boundary condition is that the gauge field A has to vanish at Z is L. So this term we already talked about, this is gone. And sine of KZL has to vanish too. So that means that since the imaginary part of the Fourier transforms A tilde have to be arbitrary, that can only be accomplished if sine of KZL has to vanish. And that gives the condition that KZ is discrete. It's given as multiples of pi over L, where the multiple we express as m is just a number in the integers. Let us now revisit the corresponding path integration for fields that in particular have the condition that their real part in the Fourier components vanishes. So while this example might not make a lot of sense, it sort of is just to press home the points of which factors sort of arise in the calculation. So don't be bothered that some of these expressions might be nonsensical. So just as a reminder, when we have normal boundary conditions, we are interested in path integrals of quadratic forms in the exponential, such as this integral here. If we Fourier transforms the field and we have normal boundary conditions, so no non-trivial boundary conditions at some locations, we can write the Fourier components, the integral in terms of the Fourier components phi of k and phi star of k, and we can separate those in their real and imaginary parts. We call the real part ak and the imaginary part bk, and then we find that the path integral is given as the path integral over the real parts and the imaginary parts, e to the minus m squared over 2 sum over ak squared plus bk squared. So far so good. If we have normal boundary conditions, the reality condition of the field phi in space implies that phi star of k is phi of minus k. And this means that not all of the components, either real or imaginary or positive or negative k, are independent. In particular, we can trade it such that we take only the components ak, bk with k ranging from 0 to infinity, but not the negative ones to be the independent components. And then we find that this path integral is written as a path integral over ak and bk with only positive k, and e to the minus m squared, because we have both k's positive and negative, so it's a factor 2 here, ak squared plus bk squared. Each of the path integrals ak and bk is then of the form given in equation 14.8. So it is a product of k from 0 to infinity of the square root of pi over m squared. Again, this doesn't make a lot of sense, but it's just to track the factors. So taking together, we find that the path integral over the field phi, because it has both ak's and bk's, gives us 2 of these components. So we get a product of square root of pi over m squared squared. That's the same as having the product going from minus infinity to plus infinity with just the square root and no square in there. And that is the same as e to the minus 1/2 because of the this should be plus 1/2, or it should be m squared over pi. But it's a 1/2 because of the square root. sum over all k is unrestricted from minus infinity to plus infinity logarithm of m squared over pi. Sorry for the typo. Okay, so that's the result we have if the integration is normal, so there are no non-trivial boundary conditions. But now we have the case that for the conducting plates, the imaginary part of the Fourier components actually vanishes. So instead of having the integral over ak and bk of this, we only have the integral over ak because the imaginary part is absent. And what that means is that instead of having a factor of 1/2, we only have half of those, meaning we only have a quarter. So that means that instead of having partition function that's e to the minus 1/2 sum over k, we have a partition function that's 1/4 because of the boundary conditions of the conducting plates. Because we have a factor 2 here for the two physical components of the field, that gives a minus 1/2 for the total result. So coming back to our actual calculation, we find that the logarithm of c is now minus 1/2 times the sum over all wave vectors in the time-lag direction, in the transverse spatial direction, and the longitudinal spatial direction of the logarithm of k squared, where I introduced the notation that k perp squared is just kx squared plus ky squared for the two transverse directions. So if we take these extent of the plates to be large, we can take the large volume limit in the transverse direction. In this case, k perp will become continuous, and we can replace the sum over k by a continuous integral. Before doing so, however, let us remind ourselves that we can do the sum over Matsubara frequencies of the logarithm. This is something we have done in many of the lectures. In particular, if you want to look at lecture 6, you can see how that works out. And we find that the sum over the Matsubara frequencies of this logarithm gives us the following expression, where now we have beta square root of k perp squared plus k squared over 2 and a logarithm. In order to keep the technical difficulties as a minimum, we now want to consider a particular case where the temperature of the field is very low. So small temperature means large value of beta. Large value of beta means this term here dominates with respect to the logarithm. So in the low temperature limit, only this first term contributes. So in the low temperature limit, we have that the logarithm of the partition function is minus beta over 2, sum over the transverse wave vectors and sum of the longitudinal wave vectors of squared k squared plus kz squared. The values of kz are discrete, so we parameterize them as m pi over L, and we sum over all integers m, so from minus infinity to plus infinity. Using now the fact that the transverse plates, the extent of the plates can be taken to be large in transverse direction, we now replace the sum over the transverse wave vectors by continuous integral. So we get the integral over k perp times the transverse volume. So this is the area of the plates written as v perp. The integral over k perp of a square root in this form is similar to a function that we already discussed. In particular, we have dealt with this function called phi back in lecture 10. The function phi was defined as this. It's a d-dimensional integral over k of something that's k squared plus m squared to the power of minus a. That's precisely the form we have now. And the advantage is that this function phi can be evaluated analytically in terms of gamma functions for any combinations of d, m, and a. And this was the result we found back in lecture 10. So in the case where we do dimensional vectorization to deal with the divergences, for the function we have at hand, we want to plug in d is 2 minus 2 epsilon and a is minus 1/2. A is minus 1/2 means that this is just a square root, and d is 2 means that we have a two-dimensional integral. That's precisely the form we want to calculate here. So we have a square root and we have a two-dimensional integral. So if you plug this in, we find that the logarithm of the partition function is beta the area of the plate V perp over 2, the sum over m of whatever this result is, and that's just 1 over 6 pi m squared pi squared over L squared to the power of 3/2. Now we can realize that in this expression, the zero mode of this sum doesn't contribute because we have a 0 here. And since it's a sum over m squared, the negative and the positive m's contribute exactly the same thing. So we can rewrite this as a sum from just positive m's 1 to infinity times a factor of 2, because we have the same contribution from negative and positive m. So we find that the logarithm of z is beta area of the plate V perp times this particular sum here. In order to evaluate this sum, let's recall that we have a function called the Riemann zeta function that's just defined as the sum over integers to some power s, that's zeta of s. In terms of the zeta function, if we rewrite our sum here, we find that we have a sum of m to the 3. This sum is not convergent, but we can nevertheless write it in terms of a zeta function where now obviously the argument is negative. So we find that the logarithm of the partition function is given as this expression with zeta of -3. And we can sort of simply use the fact that the, or not simply, we can use the fact that the zeta function, when analytically continued to negative arguments, is essentially the same as doing dimensional regularization. This is a well-known point to those that know it well, but essentially we can just plug in zeta of -3 and find that this is just a number, even though we are dealing with, in principle, a divergent sum. It's the same type of regularization that we do when we do dimensional regularization. So this clearly simplifies our result. We get that the partition function is just a finite result. It's beta, area of the plate, pi squared over 720, L to the -3. We can calculate the pressure, so-called Casimir pressure for the system. It's given as 1 over beta times the derivative of the logarithm with respect to the volume. Since the plates are very large in the transverse direction, that derivative with respect to the transverse direction just cancels out, and we find that we have 1 over beta V perp, just the derivative of the logarithm with respect to L, the size of the, or the distance between the plates. And that just gives the following result here. So that's our Casimir pressure. The end result is that P is minus pi squared over 240 L to the 4. The pressure is negative. It corresponds to a force per unit area. That's just the dimension of a pressure. So we can figure out that the force, corresponding force, is negative. So if we have our area of the plate V perp, that means that the force per area, V F over V, is just minus pi squared over 240 L to the 4. And because the force is negative, that means that the force on the boundary plates is attractive. We could have figured this out before by saying that we have negative pressure means that the system, instead of basically pushing against us, sort of tries to suck in stuff because the pressure is negative. It's the same physical effect. We can, of course, put in real units, SI units. The force per unit area in SI units just has to carry an h bar c in here, and we can plug in the numbers and find that the force per unit area is given as about 1 times 10 to the minus 7 Newton square meter per L to the 4, where L again is the separation between the plates. And from this, you can see that if, for instance, the transverse area of the plates is sort of order the separation of the plates, then we have something that goes like m squared over L squared. So this force will be very small unless the distance of the plates is tiny. And that basically also says that this is a quantum field theory effect. So we need to have very small microscopic systems in order to test it. If we take L to be on the order of nanometers here, then we would get meter over nanometer squared. That's 10 to the minus 18. So that will bring the force down to 10 to the minus 9. That's again assuming that the transverse area of the plate is about the same size as the distance between the plates squared. This calculation, this force on the plates, is a prediction from quantum field theory. It doesn't come out from any sort of classical treatments. It's really sort of the existence of the, if you want, so vacuum fluctuations in conjunction with non-trivial boundary conditions. Of course, people have looked for this. There are high precision experiments, for instance, the ones that are given in this PRL here. If you click on the link, that will bring you to the actual paper. And it has basically been nicely confirmed in high precision experiments. This is a plot from this particular paper where the data is sort of given. Okay, this is the force as measured in units of 10 to the minus 12 newtons as a function of the separation. The dots are the data points. The solid curve is the calculation for the Casimir force that's coming out of the quantum field theory treatment. So you can see nice agreement between the force and the data. The only thing that I should point out is that this is a measurement that was not done for the two-plate system. Instead, the experimentalists chose to do a system that has a plate on the one hand side and a sphere on the other side. Basically, it has to do with the fact that getting two planes at small distances to be exactly parallel to each other is very hard experimentally. So having a plate and a sphere is much easier. That also means that the calculation is typically much harder. So I have chosen to sort of do the easier calculation. But anyways, so that basically is the separation. This would be our parameter L in nanometers, and that's the corresponding force here. So you can see that there's a nice confirmation of this effect, which again strengthens our acceptance of the tool of quantum field theory. This concludes the present lecture.